My definition of what is chemistry. Now, this is my definition of chemistry. Your definition may be slightly different. If you have a textbook, the definition in the textbook will be slightly different. There's different ways to define chemistry. My definition is chemistry is the study of the composition and the structure of matter and changes that occur in matter. It's a short little definition, but basically what we're trying to say here is that chemistry is studying the composition of matter, and as we react things together in a chemical reaction, how does that matter and the structure of matter change? Because we have the word changes here. So I'll give you a good example. We take sodium, right, which is a metal on the periodic table. We're going to talk about the periodic table in a minute. It is a metal that is so reactive that if you drop it into a bowl of ice water, it will catch on fire. It will have a chemical reaction with the water, and a lot of heat will be created, and there will be a flame that is actually produced as part of that. You don't want to be eating any pure sodium. And then you have chlorine, right? Chlorine is a kind of a yellowish looking gas that will kill you. If you inhale it, you die, okay? Sodium and chlorine obviously are two totally different things that are not seemingly related to each other. Now we're going to talk about this in a minute. Why does sodium have the symbol Na? We'll talk about that in a little bit. Sometimes the symbols don't exactly match up with the letters we use to represent them. But if you take sodium and you combine it with chlorine, these are two things that basically would kill you. If you swallowed pure sodium, you would have some sort of reaction in your stomach. It wouldn't be pleasant, I promise you. Chlorine will kill you. But whenever you mix it together, it forms something new, bonded together, called sodium chloride. And sodium chloride is what you eat every day in table salt. Not only is table salt tasty, but it's actually required for your body to function properly, because when you eat the salt, your body breaks down the sodium and the chlorine into microscopic quantities that won't hurt you, but those sodium and chlorine entities in your body, they are used in the function of your nerves and your brain and all manner of uses inside of your body. But the point I'm trying to get at here is sodium is something you don't want to eat, chlorine is something you don't want to eat, but together sodium chloride has a totally different character. It is a crystal that is kind of shiny. You've seen what salt looks like under a microscope, right? It's a little shiny little crystal, but it's perfectly fine to eat. In fact, we need it to survive. It's salt, right? So when you put things together, the atoms are rearranged into some product that has a totally different set of characteristics compared to what goes into this guy, right? And this is what I called a chemical reaction. As we recombine things in different ways, we have new products that are formed, which we then can use, and that have different properties than what we started with. All right. What about, I'm just going to write it in words, wood burning, right? So what I mean by wood burning is there are chemical compounds. We'll talk exactly what the word compound means in a minute. Inside of wood that contain long chains of carbon, right? Lots of different ones. And whenever you add oxygen to wood, of course we have an atmosphere full of oxygen, and you add heat to it, we get the familiar idea of burning wood, right? And what do you get when you burn wood? You get a new rearrangement of what you had started with. You get CO2, which is carbon dioxide gas, but you also get H2O, which is water. Almost everything that burns that has carbon in it is going to produce carbon dioxide and H2O water. We're going to talk a lot in the future as to why these things are almost always produced. But the point is wood doesn't look anything like a carbon dioxide, which is a gas. Wood doesn't look anything like water, which, as it's floating up from the campfire, is a gas. But when you combine it with the oxygen and you add a little bit of heat, those atoms that are in the wood, the carbon and the hydrogen and the other things that are in the wood, they can be combined with the oxygen from the air and rearranged in a different structure than what we started with, and that has totally different properties. Carbon dioxide is a colorless gas that floats away. Of course, we breathe out carbon dioxide as well from the respiration of our own cells, which produce carbon dioxide as a waste product as well, much like wood burning. And it also produces water, which of course is totally different as well. So these products are a rearrangement. So we say chemistry is the study and the composition of structure of matter and changes that occur in matter. The changes that occur are because the atoms rearrange themselves and form new products with different properties than what we started with. All right, another example would be iron rusting. Right? If you take a a bar of iron, throw it in the yard. Iron might be, very shiny when you first get it. If you polish it really good, everything looks great, and you throw it in the yard, leave it there for a few weeks and go back, then the iron bar will not look beautiful anymore. It'll look a little brownish, a little bit maybe not as lustrous as it used to be. And if you start scraping at it, that brown substance will kind of flake off. That's iron oxide, right? That's the iron that has now been combined with oxygen to form something new, iron oxide. And that iron oxide is not strong and doesn't have the same properties as the pure iron. It is different properties because it's now combined with oxygen. So it's a rearrangement of the atoms, right? And then of course we have the famous, the big one, the super important one, we have hydrogen, right? And then we add to it oxygen, right? And of course we add a little heat, and what do we get? We get H2O. And this is rocket fuel. Hydrogen plus oxygen gives you water, and you also have heat that comes out of there, and the water is expelled out very forcefully, and so you have an explosion that's basically going on as well. All right? So that is what chemistry is. It's a rearrangement of these things that we haven't talked about yet, but they are atoms, and they are the most indivisible, I shouldn't say indivisible, they are the most elemental, fundamental thing that everything around us is made up of. And that brings us to our second definition. What is an atom anyway? It is the smallest elemental unit in a sample of matter that retains its identity. And that sounds weird. What does it mean to retain your identity? What I mean by that is a long time ago, people saw carbon dioxide, they saw water, they saw carbon monoxide, they saw sodium chloride, they saw all of the things that existed in nature, and they all look like completely different substances, right? Because water looks totally different than hydrogen and oxygen. And so obviously they thought they were totally different things. But after a lot of investigation, we figured out that everything around you, all of the very different things that we think are so different around us, are really just a rearrangement of these little, at the time they thought they were indivisible. We'll talk about that in a minute. But these small little indivisible things, which we call atoms. And now we know that there are about 100 different types of atoms. In reality, there's about 118 that we have created because the really heavy atoms are not really naturally occurring. We have to create them in a laboratory, and they don't last very long. So at the very end of the periodic table, the very heaviest atoms are things that are not really very stable. They don't exist in nature. Maybe they're radioactive. So you can count those if you want, but they're not things that we're going to study in this class. In the bulk of the periodic table, it exists of about 100 elements that are natural and stable. And the point I'm trying to make here is that all of the things that look so different around us are really just different combinations of those roughly 100 different atoms. Of course, there's a few more in reality that we've discovered, but those are the ones that are common, right? Nickel, iron, hydrogen, oxygen, chlorine, I can go on and on, lead, those are the atoms, which were also called elements on the periodic table. Those are the fundamental things that, what do we say? Smallest elemental unit in a sample of matter that retains its identity. What do we mean by that? If I take a sample and start cutting it in half and cutting it in half and cutting it in half, like a bar of pure aluminum, let's say, I cut it in half and cut it in half, eventually I'm going to get down to a single aluminum atom. And that atom, we're going to learn a whole lot more about how atoms, our modern theory of how atoms are constructed later. But for now, just know that if we try to take that atom of aluminum and break it in half, then we don't have anything that behaves like aluminum anymore. So we have something smaller than an atom in that case. So we say atoms are the smallest elemental unit in a sample of matter that retains its identity, because if you get down to a single aluminum atom, it has all the properties of aluminum. It's shiny, maybe it conducts heat, maybe it doesn't, or whatever the element is. It has all of the properties of that substance. But if you take a single atom and try to break it in half, then it has no characteristics of aluminum anymore, because you're now digging inside of the atom. Now I'll clue you in, because I know that you already know anyway, and we're going to get into this a whole lot more later. We now know that most of the mass of the atom is concentrated in the center of the atom, called the nucleus, and those are where what we call protons live and neutrons live. We're going to talk about this a lot later on, so let's not get bogged down in it right now, but That is what is in the center of the nucleus, right? And then we have the electrons, which are kind of orbiting, and we'll talk a little bit more about orbiting later, but they're in a cloud that surrounds the nucleus, and together the nucleus plus the electrons form the atom. So if you try to split the atom in half, then you don't have aluminum anymore. You have something else, because you now have kind of digging into the nucleus to the root of the protons and the neutrons that are in there. And so those are called subatomic particles, protons and neutrons and electrons, because they're smaller than an atom. Now, back in the day of early chemistry, we didn't know anything about electrons. We didn't know protons existed or neutrons existed. So the definition they came up with was atoms were the smallest indivisible things that retained its identity. But now, of course, we know we can split atoms apart into protons, neutrons, electrons, and we even know now that we can actually even split the neutrons and the protons up into something even smaller than that, and those are called quarks. And I know that sounds weird, but that's a fact. We know that quarks are what make up the neutrons and the protons. It turns out electrons don't seem to be made of anything smaller that we know of. They really are indivisible. Now, all of this is our current understanding. It could all change, which leads me to my next point. I want you, as you learn chemistry, as you read your book, as you watch my lectures, I want you to learn, but I want you to also realize that we don't know so much about how this stuff works. And I want you to really absorb that, because it's very easy when you read a book to say, well, all this is figured out, I'll just learn it. There's nothing else to learn. But actually, when you dig a little deeper than the surface layer on anything, you will realize that we don't know anything about how this stuff really works. What I mean by that is a little silly. Of course, we know some stuff, but the details of how the electron behaves in the atom, we don't really know exactly the details of exactly how things behave, how the chemical bonds work, how they break, and how they form. Yes, we have theories on how they somewhat work, but we also have situations we don't totally understand. How exactly do the bonds break and form? Exactly, on a nanosecond by nanosecond basis. Those are areas of active research. How do we make chemical compounds of a certain shape and a certain size to perform a certain function? Those are things people are researching. So when you read this stuff, and when you learn this stuff, and when you watch me talk about it, and it seems like we know everything, in the back of your mind, I want you to know there's tons we don't know, and there's tons of room for you to make that next discovery. That's what I want you to know, because I want some people watching this to get excited and get pumped up and learn this stuff and take the tools and then go discover the next big thing. All right, so we've talked about what is chemistry. We've talked about atoms, right? Some examples of atoms, right? We've talked about a lot of these already. We know we have oxygen. Right? Oxygen is on the periodic table, and we're going to talk about the periodic table a little bit better, but a little bit later. The periodic table is a organizational chart that shows all of the atoms that we know about. And it's ordered, it goes in order of increasing what we call atomic number in the nucleus. So the nucleus contains the protons and the neutrons, and as we add protons in the nucleus, we get a different element. So hydrogen has 1 proton. Helium has 2 protons. And you go up the periodic table, as you add protons to the nucleus, you get heavier and heavier elements that are totally different characteristics. But that table is structured in such a way that makes doing chemistry easier. And we'll talk a lot more about that later. But we have oxygen. The chemical symbol of that is just the letter O. We have nitrogen. Chemical symbol for this, just N. So far it makes sense, right? O goes with O, N goes with N. We have carbon. Very important. C. In fact, I want to talk about carbon for a split second. You know, all life that we know about on this planet has carbon as a building block. And we're going to learn a lot about that later. The reason life is built on carbon is because carbon can bond to itself in ways that other elements can't. It can basically form 4 bonds at once, and that allows you to make very long, complex chains of carbon. And other elements can also bond in chains, but not quite as good as carbon can. There's other characteristics of carbon that make it where life it favors it, but that's the big one, that carbon can bond in ways other elements can't, and it can make longer chains. Now, the DNA molecule in your body, of course, is a carbon chain with all other things on there as well. It's not just carbon, it's other stuff too. But if carbon couldn't bond the way it could, then we couldn't have long chains of atoms, and you wouldn't have DNA, and then you wouldn't have life. So carbon is extremely important. In fact, it's so important that after you finish Chemistry 1 and Chemistry 2, we have an entire class, in fact 2 or 3 classes, that's called organic chemistry, that's only talking about the chemistry of carbon. Carbon atoms, carbon molecules. So we have an entire set of learning dedicated to learning about how carbon works, because it's so important for everyday, Earth and for life as we know it, and so on. Right? Now I do want to talk about another one here, iron. Now the chemical symbol for iron you would think would be F here, but actually, or you would think it would be I. Sorry, you would think it would be I for iron, but actually it's Fe. Now, some of these, most of the elements on the periodic table, we just pick the first letter or the first couple of letters to represent them. But sometimes the elements are totally different than the first letter, and that's because when they first started doing this stuff, they all worked in Latin. The scientists worked in Latin. So a lot of the symbols in the periodic table come from the Latin version of that material. So for instance, iron, Fe comes from the Latin, which is ferrous. Now, I'm not going to ask you or tell you to memorize, these Latin roots. I'm just letting you know sometimes some of these off the periodic table, they look a little bit weird. Another one would be sodium. You think sodium would be S or SO, but actually sodium is Na. And you have chlorine. You think chlorine would be CH, it's actually Cl. Right? So basically, the elements on the periodic table are going to be represented by a symbol, either a single letter or 2 letters, and sometimes the 2 letters correspond to the word, and sometimes the 2 letters come from Latin. So you're just going to have to eventually, through working with it, you'll remember the ones that don't exactly match the word that they come from. All right, so we talked about atoms, smallest elemental unit in a sample of matter that retains its identity, because if you try to split the atom up, then you're into the things inside. You're breaking it apart into the protons and the neutrons, and all protons look the same. All neutrons look the same. If you had a bucket of electrons, if I could just put a bucket of electrons here, they would all look the same. They don't have any difference in the character there. Only when they're combined in these ways, these different elements have different characters. All right. Now, the next thing we're going to talk about is the concept of a molecule. A molecule. A molecule is a larger unit in which 2 or more atoms are joined, which we call in chemistry bonded, together. So I know that you all have an idea of what a molecule is. It's kind of in everyday language. This or that molecule. I know that you have an idea of it because we've all heard it before you take a chemistry class, but we have to make sure we are on the same definition. And in our definition, a molecule is when you take 2 or more atoms and you join them together into their own little unit where they float around together, kind of hooked together, because these things do in some cases like to bond together, like H2O, water. They're bonded together in a unit, and that unit is called a molecule. So it's a larger unit in which 2 or more atoms are joined, which in chemistry we call bonded, together. All right, so the most famous of this, of course, is if I can write H right, H2O, right? 2 atoms of hydrogen and 1 atom of oxygen. Other examples, carbon monoxide, carbon dioxide, CO2. So 1 atom of carbon, 2 atoms of oxygen joined together as a unit which can free float around by itself, which we call a molecule. Now, molecules do not have to be different elements like this. Actually, we can have sometimes the same molecule bonded to itself. For example, if you take 2 atoms of oxygen and bring them together, they actually form a molecule called O2, oxygen gas, right? So you may have heard in the movies, in the hospital, they'll say, turn on the O2, the patient needs O2. Or sometimes if you watch NASA and rocket launches, they'll say, the O2, we're ready to go with the O2 for, launching the rocket. Because the O2 is part of the rocket fuel. It's actually what we call the oxidizer. But in any case, it's part of what goes into the engine to burn to make the rocket fuel. It turns out that atoms of oxygen really don't like to stay separated. They actually join up together and they form a molecule. They bond together in pairs And that's why we have O2. So if you've ever heard of O2 gas, that is what that means, because they are not usually separated. They're bonded together, and we're going to learn exactly why oxygen likes to do that later. Not all atoms do it, but some do. This, of course, is a molecule. You can also have nitrogen, which also likes to bond with itself, N2. Hydrogen likes to bond with itself, so it actually forms a molecule of two hydrogen atoms which are clumped together, bonded together. Chlorine is another example. Chlorine likes to bond to itself as well. So these are all molecules, right? They're all molecules because a molecule is any time two atoms really come together and hook together like this and bond together. The whole concept of bonding we need to have a whole lesson on, because that's a whole bag of worms we got to talk about. There's a lot to understand about bonding. We don't even totally understand exactly how bonding works right now. If a chemist tells you, oh yeah, I know how bonding works, they're lying to you, because really we have our theories. It goes into quantum mechanics, right? Quantum chemistry, and we have equations that predict bonding, but the actual details of exactly how it happens, we don't understand all of those details, especially for more complicated molecules than these. That's why I'm saying there's always opportunities for someone else to make the next big discovery. All right? So we have molecules. These are when multiple atoms join together, we can have the same atom bond to itself. These are still molecules. We can have different atoms come together, and these are just very simple molecules, but we can have molecules with 5 or 10 different atoms. We can actually even have molecules form a chain or even a ring. We can actually form a circle. I told you carbon can bond in very neat ways. Carbon can actually take and bond itself into a circle. Different size circles, small circles with 5 or 6 atoms, and 10 or 20 circles. We're going to talk a lot about that later, especially if you take an organic chemistry class. So that is what a molecule is. And I think I want to talk just as an aside for a second before I jump into the next part of this, because after we talk about molecules, I want to talk about chemical reactions, right? And chemical reactions are really what all of chemistry is actually about. But before we get into this, I want to impress upon you something that I really wish someone had told me when I learned chemistry, because it's really the #1 thing that's going to make chemistry understandable for you right as you get past the surface layer. Most people can understand atoms and molecules, but when you get into reactions, you start trying to understand why they're happening and why they're not happening. Why should the reaction happen? Or maybe sometimes the reaction doesn't happen, and you start to kind of wonder why sometimes it happens and sometimes it doesn't happen. Well, let me tell you the punchline to this right now. I can't give you all the answers, but I can give you a big piece of the puzzle, and I can give it to you right now in lesson #1. All right, here it is. So you know that you have protons, which are positive, right? And you have electrons, which are negative. And you know that opposites attract. So by now you should have learned that protons and electrons attract each other. And like signs repel. So 2 electrons push apart, and 2 protons also push apart. All right? I hope that I'm going to blow your mind in a second when I tell you that this a force of attraction between protons and electrons. We call it the electrostatic force. Electro because it's related to electricity because of charges. Static because there's no current flowing, but it's called electrostatic. So they're just sitting there, nothing's really happening, but they're attracting each other, right? So that big word, electrostatic, don't let it scare you. It just means electric force, right? The electric force that exists between 2 charged particles, like 2 protons or 2 electrons, or a proton and an electron, or a repulsive force between 2 electrons, that kind of thing. The electric force is millions of times stronger than the gravitational force holding me to the ground right now. I'm going to say that again because it isn't something that makes sense, and you need to absorb it because it really does govern all of chemistry. All of chemistry. And I do mean it governs all of chemistry. The electric force, the force between an electron and a proton, the attractive force that happens there, right? It's millions and millions and millions of times stronger than gravity. It is way stronger than we think of in our everyday life. And because it is so incredibly strong, then that is what is driving pretty much everything in chemistry, right? When you mix 2 things together, sometimes they don't react. And sometimes, in a different situation, different set of things you mix together, they do react to form something new. But what determines if the thing reacts or if it doesn't? It's the electric force. If the situation that you put those atoms in are in such a way that the electric force is strong enough, then it's going to rearrange what's going on, and it's going to come together, and everything's going to stick together in a way to rearrange to form the products, right? Because the electric force is what's governing all of the chemistry that's happening, the electric or the chemical reaction that's happening, right? But if you mix two things together and nothing chemically occurs, there's plenty of things you mix together and nothing will happen at all, right? Well, why doesn't anything happen? Well, it's because everything was already stable and the electric forces that were present were just not strong enough to overcome that and rearrange the things into something new, so nothing happens. It literally boils down to that. In a few chapters from now, we're going to talk about properties of the periodic table. We're going to talk about how readily does an element donate an electron or give up an electron or take an electron, right? When does that happen? How readily does that happen? We're going to talk about the boiling point and the melting point of substances. We're going to talk about how often or how much energy does it take to take an electron from one atom and move it over to another atom, right? All of that stuff comes from the strength of the electric force, right? The strength of the electric force governs everything. It governs the properties of the atoms on the periodic table. How easily do they give an electron away? How much do they want to take an electron from someone else? All of that stuff is coming from how strong that electric force is. So later on, when we tell you the rules to try to figure out what's going to happen, because all of this chemistry is happening because electrons are being shared or transferred between the two things you're mixing together, and then things can be rearranged into a new set of products, right? But that transfer of electrons, the sharing of electrons that might happen, the rearrangement that might be happening to give you the product, it's all predicated on that electric force being strong enough to make it happen. And when it is strong enough to make it happen, then it happens. But if the situation was already so stable so that, the electric forces there are not going to make any changes, then nothing happens. And all of those properties that we learn about a little bit later in the periodic table, they all come from understanding the strength of the electric forces. Because you got to remember, and I know we haven't gotten into it yet, but I know that you all know that in the center of all of these, atoms, we have little protons, right? Maybe you have more than one, right? Then you have maybe a couple neutrons that really don't have any charge at all. And then on the outside, maybe there's a couple of electrons. And we say that the electrons kind of go around and they kind of orbit. Now, there's a whole lot more to this. It doesn't really look like that, but that's the picture that we tell everyone to understand. And so we know that the protons and the electrons are attracting each other. And once you understand that the strength of that attraction is millions and millions of times stronger than gravity, then you can understand how all of the chemistry that you learn in this class is dominated by what that force is going to do. Now you might say, if it's so strong, why don't I feel it every day? I mean, I don't feel anybody pulling on me. Okay, well, the reason you don't feel it is because if you look at this atom and you zoom out, you're going to see two protons and you're going to see two electrons. So from a million miles away, then you're going to see an equal and opposite amount of charge. And when you have an equal and opposite amount of charge, what happens if you add? Just think from algebra, plus 2, and this is negative 2, because these are negative. What do you have when you have plus 2 and you add to it a negative 2? You get 0. So anytime you have an equal and opposite amount of charges, then from a distance, far away, it looks completely neutral. It looks like 0 charge because everything cancels out. But you see, in chemistry, things don't cancel out, because in chemistry, if you bring two things together, one electron may get shared between the molecules, or maybe jump from one atom to another. Then you have a charge imbalance. Then things start moving around and try to attract and rearrange themselves into a more stable configuration. That's what's called a chemical reaction. But that chemical reaction is driven by the electrons that are moving and the forces that come about when electrons start becoming unbalanced and start moving around like that. And I know I went on and on and on about it, but I got to tell you this early on, because I could go 6 chapters in and then explain it to you, but then it's like, man, that would be a wasted opportunity for you to understand that this electric force is millions of times stronger than gravity. I'll leave you with one final thing before we move on. I'm standing here in front of this camera, but the energy in my muscles, right? Just standing here, I can jump off the ground just with the energy in my little tiny puny body. I can lift myself and remove myself from this planet, but consider that every atom on this planet is attracting my body with gravity. the Himalayas, which are on the other side of the planet, they're attracting my body because of gravity, right? The center of the Earth, thousands of miles away, is attracting my body. Someone on the other side of the planet, in their car, they're attracting. Every atom on this planet is pulling down on me. But yet, I am strong enough to push up and separate myself from all of that attraction with my little bitty muscle energy. That tells you that even though we kind of think as gravity as being strong, gravity is actually really weak, right? It's really not that strong at all. And when you do the math, which I'll do for you one day, you will find out that the equation that governs gravity, which I could write on the board, but I don't want to do it too early because we got to save some stuff for later, right? It looks almost exactly the same as the equation that tells you how two electrons repel, or how an electron and a proton attract each other. The equations look the same. They have the same force. They have the same form, I mean. However, the electric force is millions and millions and millions of times stronger, right? In fact, just to give you an idea of how much stronger it is, if you remember back from math, right? If you remember back from math, if you have 10 squared, that's 10 times 10, which is 100, right? 10 squared means 10 times 10 is 100. If you have 10 to the third power, that's 10 times 10 times 10, that's 1,000, right? If you have 10 to the sixth power, that's 1 million, right? So you see what's going on? Because the number that you have in the exponent, that's how many zeros you have here. So there's 6 zeros here because of this. But the electric force is actually 10 to the 39th power stronger than gravity. That is a 1 with 39 zeros at the end. Think about it, a million is only 6 zeros after the 1. But the electric force is a 1 followed by 39 zeros. That's many, 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 many millions of times stronger. The only reason we don't see it is because we have equal numbers of electrons and protons, so they cancel each other out. But in chemistry, they don't cancel each other out, because when one electron moves from one atom to the other, you have a charge imbalance, and that causes everything to move to find its more stable positioning, which leads to what we call, when we study this stuff, chemistry. That is why chemistry is happening. That is the stuff that you could spend the rest of your life studying if you really wanted to understand it in great detail. All right? So, chemical reaction. Let's move on to chemical reaction. And then we're gonna wrap it up here. Chemical reaction is when matter undergoes a change in arrangement and or structure of its molecules, and now you know all of these chemical reactions are really happening because the electric force is so strong that if there's ever any imbalance anywhere, things are going to rearrange to get to the lowest, more stable configuration of a state. That's what we call chemistry. And of course, the big one, hydrogen, right, plus oxygen gives you water. H2O. I could write carbon plus oxygen gives you either carbon monoxide or carbon dioxide. Why does it form carbon monoxide with 1 atom of each sometimes? And why does it form carbon dioxide with 2 atoms of oxygen sometimes? Well, we're going to talk about that. It does different things in different situations. But when you combine these things together, the electrons are transferred or shared in such a way that whatever we form on the end here is a more stable configuration than what we started with. We're going to talk a whole lot more about what that means in a little bit. All right. Moving right along, we talked about molecules, we talked about chemical reactions. Let's move back over here to the beginning. I promise we're almost done here. Let's talk about elements. Now, I know that you've heard the periodic table of the elements. You've heard me use the word elements. For our definitions, we're going to say it's the same as an atom. If you hear the word atom, if you hear the word element, they mean the same thing. For our point of view, I'm not saying there could be some other situation down the road where you might have something going on different, but for us, if I say, here is an element of the periodic table, in your mind, you want to say, well, that's just a different kind of atom. That's a unique atom that we have listed on this thing called the periodic table. Common elements, you already know. We have oxygen, we have nitrogen, we have sodium, right, which goes into table salt, sodium chloride. We have argon, and we also have things like neon. You might see those neon signs, that glow orange or whatever, right? So we have all of these different symbols on the periodic table. We call it the periodic table of the elements. You could also call it the periodic table of atoms, because elements and atoms are the same thing. Okay, moving right along, we have discussed this before, but we're gonna dot our I's and cross our T's right here. we have the idea of a compound. Right? A compound is basically a molecule with two or more different elements. You might say, wait a minute, how's that different than a molecule? Let's go back to the definition of a molecule. That's why I wrote everything down. A molecule is a larger unit in which two or more atoms are joined, bonded together. And we gave lots of examples. So a molecule is anytime, a molecule is like the general class of what's going on. A molecule is anytime you have two or more things coming together in what we call bonding. Almost everything in chemistry we study is some sort of molecule. Not always, but very, very often, right? Let's give a couple of examples. All right, let's talk about CO2. This is carbon dioxide. One atom of carbon, two atoms of oxygen bonded together. Now, this is a molecule. How is it a molecule? Because it's two or more things that are stuck together. Anytime that happens, it's always called a molecule. But this is also called a compound. Why? Because these two elements that came together were different. When they're different, we call it a compound that comes together, right? What about the famous H2O, right? This is a molecule. I'm going to put little quotation marks. It's a molecule. It's also a compound because it's a molecule because it comes together two or more different things. And because they're different elements that come together, it's called a compound. What about the famous H2O2? You know what that is? H2O2 is hydrogen peroxide. You use that to clean cuts, right? It is a molecule because it is anytime two or more things come together. Notice we have four atoms here, two atoms of hydrogen and two atoms of oxygen. So it's four atoms here, but it's also a compound because it's different elements. So you might say, well, wait a minute, everything you've listed here is a molecule and a compound. So when can it be different? Let's talk about the oxygen molecule. Just call it O2, right? Well, this is a molecule because it's two or more things stuck together, but it's not a compound. It's not a compound, right? The reason it's not a compound is because it's the same element stuck together. It's only a compound when it's two or more differently named, different items that come together, then it's called a compound. These are different and they're stuck together, so it's a molecule and a compound. These are different. They're stuck together, so it's a molecule and a compound. These are different, so it's a molecule and a compound. These are the same atom, so it is a molecule, but it's not a compound, right? What about nitrogen gas, right? Same thing. It's a molecule and not a compound. What about chlorine gas? Well, it's a molecule, but it's also not a compound. So I just want you to remember, most of the time, things that we study are compounds. Because most of the time, the things you're studying are not the simple ones like oxygen gas or nitrogen gas, O2, N2, Cl2, H2, hydrogen gas. Usually, we're studying other things like methane or something like that with lots of different elements in there, so that we almost always call them compounds. But just so you know, it's only really a compound if the things that are made up of that molecule are different items. Learn anything at mathandscience.com.